Okay, last few lectures, I mainly discussed about this magnetostatics, and you may already found that we did it very similar to the electrostatics. We electrostatics we have the charge, we have the electrical field, and we have the vector potential, and we have the scalar potential. We figure out what is the relation between all these three variables. Once give you rho, how to calculate E. Once you have E, how do you figure out the potential? Once you have a potential, how do you figure out the charge distribution? So similarly, what we did it for the for magnetostatics. So we have current, we have the B field, and we also have the vector potential, and we also described, how we go from one variable to the other variable. Okay, so you can really look at these two chapters, and you find that they are very similar to each other. Okay, so only we didn't spend another chapter to talk about the potential. Okay, so the main reason is the vector potential is not that useful compared to the scalar potential, and also the equation that we really need to solve is a Poisson equation, so which is generally harder than the Laplace equations that we often need to solve for the scalar potential. Okay, so now I wanted to do exactly the same thing. I wanted to talk about the magnetic fields in matter. So this is, we already spent one chapter to talk about the electric fields in matter. Okay, so as you know that for the electric field is mainly, we have, for example, neutral atoms, and because of the applied electrical field, and then the nucleus will be moved slightly different away, for example, from the center of the electron cloud, and that created a dipole. Okay, and this dipole, so it should be this, I think it's this direction. It'll create a dipole, and the atoms thus becomes polarized, and then we described the phenomena, and we also talk about what is the electrical field of a polarized object, and then we introduced this electric displacement, that include the effects that are due to the applied electrical field, and also due to the bound current. Okay, bound charges. Okay, that are due to the polarized objects. So similarly, for the magnetic fields in matter, we will discuss, the same set of things. Okay, so here for electrical fields in matter is mainly due to the dipole that are created, and in the for the magnetic one is really these atoms. You have electrons, and they can spin, and it will create some magnetic dipoles. Okay, or you can have electron that circulate around the nucleus, and then create a small current loop, and then also created a small magnetic dipole. So when you have a lot of these tiny magnetic dipoles, and then we apply some magnetic field, external one, and that will also cause these materials to be magnetized. Okay, so we will first talk about magnetization for different materials, and then after that, once we know an object is magnetized, we wanted to also figure out what is the magnetic field there. there we also will introduce the boundary surface current and also boundary volume current, just like what we did for the polarized objects. We introduced surface charge and also the volume charge. So we will do exactly the same way for the magnetized object. And then, of course, once we have the object magnetized, it also creates some magnetic field. So it will change the original B field value. So we will define a new variables, called auxiliary field H. Okay, so we will spend the next probably 2 lectures, to discuss about, the magnetic fields in matter. Okay, so we first talk about magnetization. Okay, as I said, for the magnetic, as we discussed in this magnetostatics, we create this magnetic field. So they are mainly due to moving charges. That is also we call it currents. Okay, so there if we look at really these materials, we look at the atomic level. As I mentioned before, we have electrons. They can orbit around the nuclei, and also electrons can also spinning about their own axes. And we can treat each of these as these tiny current loops. Okay, so if there are current tiny loops, as you know, that will create the magnetic dipoles, which is often this the current times the area of that tiny current loop. Okay, but for most of materials, okay, because the atoms orientations are random, due to these thermal activities. So these small tiny current loops, they often cancel with each other, so there are no macroscopic effect for the magnetization. However, when we apply an external magnetic field, so what happened is these tiny dipole moments, okay, will be aligned together, and then will create an overall net alignment, okay, of these dipoles. Okay, so that will create some macroscopic effect about magnetization. Okay, so sometimes we say this material become magnetized. Okay, so there are 3 different phenomena that we have for different materials. We categorized something called paramagnetism. These are the magnets. They will once you put inside a magnetic field, it will also create a weak magnetization, and this magnetization is aligned with this with the applied magnetic field. In other words, that they are parallel to each other. Okay, so this is a parallel. So it will create its own magnetization, and is parallel to the external B field direction. Okay, so now of course, if the field is removed, and then this magnetization also removed. Okay, just lost that magnetization. Okay, so this is what happened. Then the other one is called diamagnetism. Okay, so this kind of materials, once we have external B field applied, it will create a weak magnetization. However, this magnetization is anti-parallel. Okay, to the external B field. In other words, it is opposite. The direction is opposite to the external B field direction. And also, once the external B field is removed, and then this material just loses, its magnetization. Okay. Then we also have the third material called a ferromagnets. Okay, so this kind of material, that they can be aligned. They have dipoles that can be aligned with external magnetic field, and it will produce a even stronger magnetization. But the most the most important thing for this kind of material is, they still retain the magnetization even after the external B field is removed. Okay, so this is as I said, this is really material still retain the magnetization. Even if B is removed. Okay. Okay, so it's kind of, sometimes we call it a permanent magnets. Okay. So I will first discuss these paramagnetism and diamagnetism, because they are relatively simpler, and we don't need to consider the strong interactions between these magnets. Okay. Okay, so I will first talk about the paramagnetism, and then I will talk about the diamagnetism, and at the end of this chapter, and we talk about the ferromagnetism. Okay. As I described earlier, that the reason the material can be magnetized is mainly due to either electrons that that are circulating around the nuclei, or the electrons they are spinning about their own axes. Okay, so in other words, it creates these tiny current loops. Okay, so so in other words, that we want this is a kind of like the magnetic dipoles. Okay. Okay, so that is why we wanted to study what is the torques and also forces on magnetic dipoles first. Okay, so in other words, that we have a magnetic dipole, and we put inside a magnetic field, and see what kind of torque and what is the behavior, what kind of forces applied on it. So to do that, we wanted to consider the rectangular shape, because it's often easier to calculate it. Later you can see, and we can consider each current loop to have a very small rectangular shape. And why we wanted to make it rectangular, you can think about that. So if each tiny ones together, okay, and you can see that these two, the two neighbor sides, they will cancel each other. This current goes this way, this current goes the other way. The same thing, from this side. So they kind of can be, they cancel with each other. So at the end, if this way, you only kind of have a current that goes this way. Okay, so in some sense, any of this current loop, any shape, okay, we can use it. We can use this infinitesimal rectangular shapes to build it. We just needed to put many of them together, okay, and we can build any current loop, okay, because all these internal size, the currents just cancel with each other, okay. So that is why we wanted to study this rectangular shape current loop first, okay. So now let us we put this rectangular shape, this current loop, inside a magnetic field, and we see how what are the forces and the torques that are applied on it. So let us consider this one. So let us consider this XYZ direction, and the B field is just along the Z axis. Okay, now let us consider a rectangular shape. Okay, let us put it this way. Because we don't really know the direction. Sorry, I should really let it center. Let it center around the origin. Okay. And this one is really center is located at the origin, but there is tilted. Okay, let us consider more general case. Tilted, in other words, that if we find the normal direction, okay, which is the current, let us say this is a current that goes through this loop, and this of course is the magnetic dipole moment direction, because m is really I times the area direction. Okay, so let us consider this angle is theta. Okay, so let us consider the length here is b, and the length along this side is a. Okay, so now what do you find that so because there are current that goes through, so then according to the Lorentz force should be Lorentz force law. So there are forces, you can see that one is let us consider the two sides with the length that is a. So what happened, you can look at this right hand rule, like a qv times b, and you will find the two forces on this sloping side. The two forces, they are equal, and they are opposite to each other, and there are no general torque applied. Okay, however, if we consider this horizontal side, so is these two lines. Okay, means the current goes this way. What you will find, okay, so if I really write it down, let us look at it this way. So now let us consider it is, if we saw it this way. Okay, we so this is just the side A. Okay, if we see, watch it this way in the xz plane. Okay, so what do we have z? We look at our yz plane. Okay, so what happened is from this side there is a force, okay, that are applied on this side. Okay, and there is another force that is applied on the other side. Okay, so this is what happened. So the two forces, they are equal to each other, they are also opposite to each other. However, because this is the origin, however, these two forces will generate a torque. Okay, so how to calculate the torque? Okay, so if you think about that, if you look at this, so this angle is really theta. Okay, so you can, so the two side, this is O, so the length is A over 2. So this is the theta angle. So the torque is really this F times this length. This length is A over 2 times sin theta. Okay. And there are two of them. One is applied this way, one is applied the other way. So there is another 2 there. And you also can figure out, torque is really R cross F. Okay. And R direction is this direction. Okay. So R cross F is really along the X direction. Okay, so in other words, that the torque is really A F sin theta x hat. Okay, so this is the overall torque that the magnetic field will create on this tilted rectangular shape current loop. Okay. Okay. So now let us look at what is the force. Okay. What is the magnitude of the force, on each of these horizontal segments. Okay, so the force, as I already described before, the force is really, the dl cross b. Okay, you can look at the formula that we have for this Lorentz law. So what happened is, because the B field is the same and the direction is also the same, so at the end is really just dl. Okay, that the force is along the y direction. Okay, and then this dl, okay, is really just the length, okay, of this segment, okay, which is y. Okay, which is b, small b. Okay, so from here you can see that the magnitude of the force applied on each of the horizontal segment is really this I capital B times the small b, which is the length. Okay, so from here you can see that this n is really, we just put this into this. So what do we have? I, we have AB, we have this capital B, we have sin theta x hat. Okay, so you remember that the magnetic dipole is really the current times the area, okay, of this current loop. So in some sense, this is really the magnitude of the magnetic dipole times mb sin theta x hat. Okay, so if you look at really the direction, sin theta mb, it looks like a cross product. And if you look at the direction, okay, it's really m cross b. Okay, you can see that m direction, okay, cross b direction tell you that is x hat direction. Okay, so you can see that for the amount of torque, okay, that are applied on a rectangular shape magnetic dipole is really just this m cross b. Okay, so we derived this formula. Here we assume that it is a uniform magnetic field. B is uniform, around this area. Okay, but for a non-uniform magnetic field, you can also derive it the same way, and you will find that it's also the formula will look exactly like this. Okay, and also you can see that the torque direction, the two forces are applied this way. Okay, the two forces applied this way, so then it will make this theta angle becomes smaller until it becomes 0. Okay, so you can see that in that case, this dipole moment direction will align with this magnetic field direction. Okay, so you can see that the torque is really in such a direction as to line the dipole up parallel to the field. Okay, so this is will make this magnetic field stronger. So this is what we call it a paramagnetism. Okay, so you can see this is really just you can think about that is really the electron that are spinning around, create this tiny current loop, and then when the magnetic field is applied, and each of this current loop suffers this torque, and the overall effect of this torque is to line this dipole up, parallel to the direction of the external magnetic field. Okay. Okay. So of course, you can think that because electrons is always spinning. You think that this effect should happen for all materials. Thus, all materials should be paramagnetism material, paramagnets. Okay, but what happened is, if we really here is really the classical picture. So if you really look at these materials, you need to consider quantum mechanics effect. So for quantum mechanics, especially about this Pauli exclusion principle. So these electrons for a given atom, electrons tend to be paired together, and the electrons, they are paired together with opposite spins. Okay, so you can think about that. So what happened is, one is spin up, then the other one tends to be spin down, and in some sense, these effects will neutralize, the torque on this combination. Okay. So in other words, that for material, if the electrons are paired together, then it will not suffer from this torque, and then this paramagnetism effect will not really show up there. It is only for the atom or molecules, where they have an odd number of electrons. Okay, so in other words, this extra unpaired electron will suffer this magnetic torque. Okay, so in other words, this paramagnetism effect, will only happens for the molecules, or atoms, with an odd number of electrons outside. And of course, for materials, we always have these thermal collisions, the atoms or molecules, they randomly walk around, and these random thermal collisions often tend to destroy the orders of these magnets aligned along the magnetic field direction. Okay, so here just show you that if there is a magnetic dipoles, and if we put inside a magnetic field, it will suffer this torque. Okay, so now let us look at what are the amount of force that are showing there. Okay, so the force is really, if it's magnetic, if it's uniform field, and as I showed in this case, these two forces, they are parallel to each other. They are equal and they are opposite sign. And the same thing, for this side, the force, they are equal to each other. They are opposite and equal to each other. So for the uniform field, okay, the amount of force that the magnetic dipole, that will experience will be zero. Okay, while if they are non-uniform field. Okay, so it showed that let us consider a toroid. There are some loops that are current that loop around, and it will create this magnetic field, which is often this kind of directions is non-uniform. Okay, so now if we put here, if we put so here I use a circular shape. If we put a magnetic dipole here. Okay, then what happened is you can think about that, if the the dipole is look like this, and let us consider at this age the B field has some directions, okay, with respect to this. So if it's this theta angle, the current for this case we are just pointing into this page, okay. So now we know the F is really equals to I times this dl cross this B. Okay, so dl is pointing into the paper, the screen, and the B field is pointing, there are some directions there. So what happened is, if then you can use the right-handed rule, and you see that the force, will really look like this way. Okay. Okay, so this one is really, this one will be this dl times this B times this cosine theta. Okay. Okay. This cosine theta. So what happened is, so this is I, so this dl, is really just the radius of this loop. Okay, 2 pi r times B times cosine theta. Here is the magnitude of the force, and the directions, you can see that is a point toward to the bottom. Okay, that means that there are some angles there. Okay, pointing downward. Okay, so this is just what happened, just for a non-uniform field. It will look like this. Okay, so then of course, we wanted to have a general formula to do this. To do the general formula is we often wanted also to calculate what is the potential energy of this system. Okay, so this one I don't want to really describe it. I just wanted to say that if we have the magnetic dipoles that are put inside a magnetic field, and then the potential energy is just right, is minus this m dot b. Okay, so this gives us the potential energy. Okay, so of course once we have a potential energy, we can also derive a force. The force is just minus del u. Okay, so so this is just a potential, this is just the potential force. Okay, so if you add together in them, these minus signs just cancel with each other. So the force, will just take this formula. Okay, so this is what happened if we have a very infinitesimal current loop with magnetic dipole moment of this m. If we put it inside a magnetic field, then the overall force applied on it is just to take this formula. Okay, so you can really confirm, the two cases, that two special cases I described here really satisfy this formula. Okay, so this one is actually, if you still remember the dipole, okay, the amount of force that for dipole, the electric dipole that are inside electric field, and the formula look like this: P dot E. Okay, so where P is really the dipole moment. Okay, so here is plus and minus. So here is the electric dipole. Okay, that are inside electric field. Okay, then the amount of force applied on this dipole is like this. So you can kind of think about that, there for the magnetic dipole. Okay, you may say, maybe we can also treat something like this, just like what we have for the electric dipole. So this is called a magnetic dipole. Okay, you can think about it this way. Okay, We have magnetic south pole, and we have a magnetic north pole, and the direction pointing from the south to the north. Okay, we have this is a direction. I mean, of course, this picture is really wrong, because we know that we don't really have a single magnetic north pole or south pole. Not like electric dipole, we can have a positive charge or have negative charge. But for the magnetic field, we don't really have that. Okay, but this is still a picture. You can think about to solve some problems, or many people just use this sign to indicate, you know, there are some currents around. In a current loop, it will create the magnetic dipole. Okay, so I just say, this one is more commonly used. Okay, to indicate what is a magnetic dipole. Okay, if you think about it this way, it will be very similar to the electric dipole. Okay, anyway, you can see that the force for a magnetic dipole in a magnetic field, and for electric dipole in an electric field, the formula, they are very similar to each other. Okay, so this is what we explained for the paramagnetic material. Okay, now let us consider the diamagnetic material. Diamagnets. Okay, so this one, what we really think is really, as you can see, that this is mainly due to effect of a magnetic field on these atomic orbits. Okay, and we said for the paramagnets, we mainly have the electrons spinning around. Okay, create these dipole moments. Okay, so here we kind of say that we have nuclei. Okay, and we have electrons that are revolve around the nucleus. Okay, so this one, of course, will also create a current. Okay, so this one is just that electron itself spin around. Okay, here the electron is moving around the nucleus. Okay, so now we also wanted to figure out what is the dipole magnetic dipole moments here. Okay, to do that, we need to first figure out what is the current. So the current, you can see that is really charge divided by the time. Okay, and we know that the electron, let us say the radius is r. Okay, and the electrons is moving with a speed of v. Okay, and we know that the period is really is 2 pi r. It is the length of this circle divided by the velocity. Okay, so that tells us how much time it takes for electron to move one period. Okay, so we can put it together. So the minus ev divided by 2 pi r. Okay, so this is the amount of current. Okay, we have minus e because the electron charge is negative. Okay, now once we have I, we really can figure out the dipole moment. Okay, the dipole moment is really I times the area. Okay, let us say if we see that this is the z direction. Okay, so this one is just along the z direction. Okay, so this is really I times 2 pi r square. Okay, which is the area of the circle. Okay, so if you plug in r here, you have minus 1/2. Okay, e v r. Okay, so here is the what happened, for this, due to this atomic orbits. Okay, and it will also create another dipole moment. Okay, so in other words, we have two. The first one is the electron spinning around create a dipole moment, and then at the same time the electrons move around the nucleus, and that orbit also create a dipole moment. Okay, so this dipole moment, of course, will also suffer a torque. Okay, just like what we have described for this paramagnetism. Okay, so however, it's a little bit harder to tilt this entire orbit. Okay, than it is to the spin. Okay, so in other words, that this effect actually is small. Okay, this orbital contribution to the paramagnetism turns out to be small. Okay. So in other words, that this one almost have no contribution. Okay, to the magnetization. Okay. However, there is a significant effect on this orbital motion. So what happened is electrons, originally, has this speed and is just move around the nucleus. Now, after we apply a magnetic field, so what happened is this electron, where you will see that it will speed up, okay, or slow down, depending on the orientation of this magnetic field, okay. So let us just show you how it is done this way. Okay. So now let us consider. Okay. Let us say that we have this circular orbit. Okay. So this is now let me put it this way. So it's a circular one, but it's on the XY plane. Okay. So the Z plane is here. Z plane. Okay. Sorry. So the Z plane is here. Okay. So now the electrons is moving around this way. Okay. And we know that the electron is really a negative charge. So the current, is really move, because current is often defined as the direction of a positive charge moves. Okay. So use the right hand rule, that the magnetic dipole moment, will look at the will be pointing to negative z direction. Okay, let us say this is the radius is r. Okay, so let us look at this classical picture. Okay, so we have an object that is just moving around this nucleus. Okay, let us consider this is E plus. Okay, E minus here. Okay, so now we have this centripetal acceleration. Okay, the force is really the electron velocity divided by r, mv squared divided by r. Is really the centripetal acceleration force. Okay, so this is really sustained by the electrical force. Okay, so for this case is 1/4 pi epsilon 0 e squared divided by r squared. Okay, so this is what we have. Okay, so it's originally electrons is just moving with a constant speed v. Okay, with a radius that is r. Now once we have additional if now we apply a magnetic field, okay, let us assume it's along b direction. Okay, and then the charge is moving. Okay, and we know that it will suffer a lot of force, which is the Lorentz force. Okay, it's qv cross b. Okay, and you can see that if b is along the z direction, if let us say velocity is moving move in this direction, and you will see that this V cross B, okay, where often is pointing outside, okay, is radially point is outward direction, okay, and because this is a negative sign, okay, the charge is minus E. So what happened is the force direction, we are really pointing toward the center, okay. Okay, so in other words, that now is me, the velocity, let us say it becomes a new value, okay, becomes v bar now, okay. So this one is this electric force plus the new force, okay, that is due to the Lorentz force, okay. So it has to be plus sign because it is also pointing along, it's an attractive force if you think about it this way. So it will look like this, okay. So now you can see that, these are positive numbers. So in other words, this V should always be greater than V, okay, the original one, okay. This is the one without the magnetic field applied, and this is the velocity once we have a magnetic field applied, okay. So now let us look at this, okay. Now let us try to figure out what is the velocity difference, okay. V bar minus V, okay. So what do we do is let us we do it this way. We move this, and we have this me v bar square minus r minus this 4 pi 1 over 4 pi epsilon e square over r square, and we said this is really just this, okay. So this is really me v square divided by r, okay. So in other words, that we have me divided by r. So this is v bar square minus v square, okay. Here we can really write it down. A square minus b square is a plus b, a minus b, okay. Often the v bar is close to the v, okay. So in other words, that this will be close to 2 v bar. So this one, let us call it delta v, okay, the difference. Now what do you see that is really E V bar B equals to 2 ME V bar R delta V. Okay. And now you see that this V bar cancels. So delta V equals to this E R B divided by 2 ME. Okay. So here is, of course, this is a positive number. So in other words, that this electron will speed up. Okay, the velocity will increase. Okay, and we said that of course, once the velocity increases, so that really means the current is bigger. Okay, because V increases, and this M, of course, increases. And we said this M, okay. So in other words, we plug into that equation, okay. M is really M depends on the V, okay. So this is really just 1/2 E delta V, okay, R the hat, okay. So this is give you minus E square R square divided by 4ME B direction, okay. So what do you see that the main thing that I wanted to say that you see that the change, because the magnetic field applied, and it will make the electron speed up, okay. So it will increase the magnetic dipole moment that are created due to this electron orbits, okay. So you will see that this increase is really negative Okay, it has the opposite to the direction of this the B field direction. Okay, okay. In other words, you can see that that this will turns out it will create the new magnetization, but these directions are anti-parallel to the B field direction. Okay, so that is really what we call this is really the diamagnetism. Okay, in other words, that we use this orbital circuit to really explain what is the dipole diamagnets. Okay, so you can see that the diamagnetism, the effects, they are often much weaker than the paramagnetism. Okay, so as we said, the paramagnetism is mainly happened for events, for atoms or molecules, that have an odd number of electrons. Okay, so you can imagine that if there are odd number of electrons, then the material will be mainly paramagnetic, paramagnets. Okay, while if the atoms with even number of electrons, okay, and the size of this paramagnetism is small, okay, so then the effect of this diamagnetism will becomes bigger, okay, so that is why the diamagnets, often happens, for materials, where the atoms have even number of electrons. Okay.